Okay. Can you see my PowerPoint or PDF? Can I see it?
Yep.
Yes, we can.
Okay, good. Thank you. Okay. So today is about RCT. So I'll talk about concepts of RCT. I know a little bit boring, however, it's very important. And then I'll show you how to use R, especially R, to do block randomization and power analysis. And then later on, we have a example paper. I emailed that to you, so I'll talk about that paper. Okay, so let me talk about RCTs. So randomized control trial actually is a research design. We call that an experimental research design. It's a type of research design. So we use RCT to study what? To study the effectiveness of a new instrument, a new therapy, a new program, a new intervention, or a new prevention. So it is considered as the gold standard. So why this kind of design is considered as the gold standard? So I'll talk about this. So the goal of RCT is try to compare two groups in primary outcomes or secondary outcomes. So at least we have like two groups. So because it's called controlled trials, we must have a control group. So we have intervention group. Also, we have a control group. At least two groups. So let's see. In experimental design, so we should have a pre, which means you collect data at baseline, and then you give people intervention. Then you collect data again. We call that post-test. So at least we collect data twice, and also we have a control group. So this is the key. We have a control group. Also, we collect data at least twice. So this is a strong research design. So why this is a strong research design? Because this kind of design has a very strong internal validity. So I'll talk about internal validity. So actually in experimental design, we can have something like a pre-intervention post without a control group, no control. I just have one group, intervention group. I collect data twice. This kind of design is not a strong design, no, because this kind of design doesn't have a control group. So in RCT, we must have a control group. So this is very important. Let's see. So this is the diagram of an RCT. So the study participants are randomly assigned to either group. So this is about randomization because it's randomized controlled trial. So your study participants must be randomly assigned to either group, intervention group and control group. So we collect data at the baseline, give people, in both groups, we give people intervention. However, the interventions are different. In intervention group, you give the main intervention. So in control group, you give people something else. IRB requires you must give people in the control group something else. It's not like, hey, I won't give you anything. Not okay. So you must give control group something else. However, it's not your main intervention. So I use intervention term. Absolutely, you can. Hey, this in my study maybe is a therapy, a new therapy, a new drug, a program. So I just use intervention term because I'm so familiar with intervention. So I use intervention because it could be anything else. It could be a program, could be a new drug, could be a new therapy, could be a new treatment. So here, this is very important. You give a control group something else. Collect data twice. So sometimes we collect data more than 2 times. So it's like I have post-test 1, post-test 2, post-test 3. So it's really like you have a longitudinal study. You want to see change over time. You have a time variable. So we also have time variable in this kind of design. So time is very important. So think about time. So hey, time is a predictor, or it is. Especially you want to study change over time. Time is a predictor. So I'll talk about that. So here, this is very clear. You have two groups, collect data twice, and you give intervention to each group. You give a control group something else. So this is design. Also, you randomly assign your participants to either group. So that's why it's called randomized controlled trial. So key points here to summarize that diagram. So we have at least two conditions. You can call them like conditions. Intervention condition, control condition. So we have at least two conditions. Sometimes you see somebody's research, we have more than two conditions. So we have like a more than one intervention group, like intervention group 1, intervention group 2. Participants are randomly assigned to either group. And the participants are offered either intervention or something else. We compare two groups on main outcomes. So when you look at the published papers in medical field, they always mention something like a primary outcomes, secondary outcomes. So in control group, your control group can be a placebo group, an old treatment group, other intervention group. So it's not your main focus. It's not your main focus. However, it is important. You must have your control group. So people in control group should be treated identically to the experimental group. This is very, very important. This is also about internal validity. So I'll talk about internal validity here. I just want to say something. When you collect data, the procedure collect data from control group and you collect data from intervention group, the procedure should be same. Should be same. This is very important. Should be same. It's not like I treat a control group differently. No, that's not okay. So in terms of data collection, and also the participants from both groups should have very similar demographics. Especially you have confounding factors. Well, what's the meaning of confounding factors is really like your key outcomes, your primary outcomes or secondary outcomes are also related to some factors, not your intervention, related to, for example, related to age. So your two groups should have the same, I say same or similar, average age or age distribution. This is also related to internal validity. So this is very important. You need to identify your confounding factors before data collection. So what kind of factors could be related to my primary outcomes or secondary outcomes? For example, your primary outcome is blood pressure. Absolute age is related to blood pressure. So in your intervention group or control groups, they should have like a same age distribution. The average age is very close. So this is also very important. So how to get identical groups, or we call that balanced groups. And this is about randomization. I'll talk about that. So the research question, when you have an RCT design, is the research question because your main focus on what? On the effectiveness of your intervention. That's your main focus, is whether or not my intervention works. This is the main research question. So it's in other words, actually, it's really whether or not my intervention group perform better than control group in primary outcomes. If perform better is like a positive direction, or maybe you have like a negative direction, depends on your primary outcomes or secondary outcomes. So the effectiveness of intervention is the main focus. In program evaluation, we also use RCT design. Program evaluation. In program evaluation, we have like different types of evaluation. We can have like a process evaluation. Process evaluation is really like you, it's not just evaluate your program. You want to evaluate your interventionists, whether or not because they conduct intervention. So whether or not they follow the protocol when they conduct intervention. So in program evaluation, the evaluation is so different. You have process evaluation, outcome evaluation. Also, you can have like impact evaluation. So impact evaluation is like a long-term effect. After 1 year, what happened? In medical research, however, is sometimes we look at long-term effect, but sometimes we just look at the short-term effect. Is outcome just like we just look at maybe after 1 month, what kind of outcome we can get, whether or not there is an improvement in my primary outcomes. So that's in medical research. So program evaluation is more complicated. However, we still use RCT. We still use that kind of design because it's a very strong design. So that's why we use RCT instead of something else. So instead of something else, yeah, absolutely, we can have like a quasi-experimental design. It's not just RCT. Hey, I have another kind of design. So the difference between quasi-experimental design and RCT is the randomization. So you don't need to randomly assign your participants to either group. Sometimes we just use a convenient sample. It's really, okay, students from this classroom, you are in intervention group. And students from classroom B, you are in control group. Just they are so convenient for you. Or just use them. There is no randomization. We don't randomly assign students from both classrooms to either group. There is no randomization. So the difference between quasi-experimental design and RCT is the randomization. Absolutely, quasi-experimental design is a weaker design. Why? Because this kind of design doesn't have a strong internal validity. So I'll talk about internal validity. Yeah, here we go. So internal validity actually is very, very important. What's the meaning of internal validity? It's really like at the end of the day, you state after you collect data, analyze your data, and then you state, okay, my intervention had effects on my primary outcomes. The truthfulness of this statement is internal validity. So it's think about the design without a control group. Without control group, all I have just intervention group. So I state, okay, after data analysis, very good. There is an improvement in something in primary outcomes. So I state my intervention has effect on the primary outcomes. Well, you cannot do that. Why? Because other factors, who knows? You don't know, I don't know. Other factors may make contributions to the improvement of your primary outcomes. It's not just your intervention, or maybe it's not your intervention. It's something else. If something else also can explain the change of your outcomes, because we have like a time variable, right? Always study change. So when something else, some other factors also explain the change of your primary outcomes, And then you cannot state my intervention is effective. You cannot say that. So this is about internal validity. So it's really like, hey, without a control group, that kind of design actually is very weak design. And that kind of design doesn't have a strong internal validity. No, because other factors, especially in social science, absolutely other factors could make a contribution to the change of your primary outcomes, because you don't have any control. All you have just one intervention group. That's the internal validity. So I want to say something about threats to internal validity. We have like different kinds of threats. The first one is reverse causation, especially in survey research, because you only collect data one time, just one time. When you collect data one time, it's not like RCT. I just collect data one time. So because when you say A predicts B, A should happen before B happens. That's the order, the time order. Then you can say, okay, A predicts B. In survey research, when you collect data just one time, and you don't have that kind of time order. So I have like several variables in my survey. Several variables in your data, actually. I say several questions in your survey. Then you say question one predicts question two. Actually, you don't have that kind of time order. However, we still can design our survey questions in a way to build that kind of time order. So for example, during last year, what happened to you? You can ask a question in that way. So reverse causation is really A predicts B, B predicts A. You see that? You are not sure who predicts who, because A can predict B, B also can predict A. Then there is no prediction, because a causal relationship is a one-way relationship, is a one-direction relationship. So A predicts B, B predicts A, then A is associated with B. There is no prediction. So be careful here. So that's the threat to the internal validity. Yes, you say, hey, my A predicts B. Actually, that's not the case. Time threat. We have a lot of time threats. First one is history. It's really like during the intervention, a big event happened, a big event. So if your design doesn't have a control group, and then it's the event had effect on the outcome, not your intervention. So that's like a history threat, like a time threat. Another one is reactivity. Reactivity is really like participants are exposed to your pretest. So basically, participants understand the purpose of the study, know your questions, because the pretest questions, pretest post-test will use same survey. Oh yeah, you must use a same survey. You ask the same questions, otherwise you cannot compare. So then on the post-test, the participants more likely to give you what you expected. It's really, hey, you expect that kind of the answer, then they give you that. So then this is a threat to the internal validity. You see here, we need to disguise the purpose of the pretest. That's not easy, because you have to tell people the purpose of your study, the purpose of your study. So they are all time threats. So next one is maturation. Especially you collect data from kids. You collect data from kids. And also your research questions related to, for example, I want to study kids' knowledge, kids' skill. Absolutely, after they grow up, they gain more knowledge, maybe about your research interest. So the change of knowledge, for example, is not because of your intervention, it's because of the growth of kids, because just normal growth. So this a type threat to the internal validity. When I talk about this time threat, is really like when you have a control group. Because I'll talk about that. Use a control group. Yeah, when you have a control group, absolutely, you can avoid all the time threats. You can avoid them. So now, just picture it. I don't have a control group. All I have is just one intervention group. So why this kind of design is a weak design? Because internal validity is not good. So another one is instrumentation. This is about data collection. So when you collect data, at the pre-test and post-test are different. The environment is different. The way you collect data is different. Then not good. Can influence the internal validity. So you need to standardize the procedure of data collection. So at the post-test or at the baseline data collections should be same. So all the time threats, you can control them. Use a control group. So I have a control group. When I have a control group, for example, this is growth, the normal growth. When I have a control group, people from both groups grow, right? They all experience same thing. It's not like I only have one intervention group. Then you cannot balance out the threat. When you have a control group, then you can balance out the threat. So that's why I here use a control group can protect against time threats because they all experience same thing. Big event, maturation, they all experience same thing. Group threats. So in the very beginning, the people from both groups, they are different in primary outcomes or in confounding factors. They are different. So this is not good, absolutely not good. That's why we need a randomization. When you use randomization, you can balance out the group threats. You can make sure the two groups, they are similar in confounding factors or in demographics. So next one is mortality, or we call that attrition. Mortality, this is very, very common in RCT research. I mean, in intervention research, in RCT design, actually. So because at post-test, you lose cases. This is very, very common. Trust me, it's very, very common. Unless you have more control on keeping your cases. So especially, for example, we collect post-test data maybe after 2 weeks or after 1 month, we collect the post-test data. Then you lose cases. So attrition or mortality cannot be prevented by randomization and a control group. It's really like we just cannot avoid this. Unless we have strategies. We push really hard to keep cases. Otherwise, it's very difficult to avoid mortality. Especially, I have a longitudinal study. I collected data more than twice. So I have post-test 1, post-test 2, post-test 3. Then you lose cases at each data collection. You lose cases. Unfortunately. So how to keep your cases is very, very challenging. Very challenging. Okay. So power analysis is about how to estimate your sample size. You need to estimate sample size. So when you do power analysis, you need to know several things. First, the value of your power, the power, alpha level, effect size, and what kind of data analysis you are going to use. You must have all of them. Otherwise, cannot estimate sample size. Or don't tell me, okay, your linear regression I can do is 5 or maybe 10 subjects or 15 subjects by each predictor. Yeah, that's okay. That's can tell you something. However, when you try to estimate sample size, when you do power analysis, so you need to know all of them. So what is a power? So it's a 1 minus beta. What is beta? Beta, we call beta type 2 error. Type 2 error. So 1 minus beta is a power, is the probability of correctly rejecting the null hypothesis when it is false. But when null hypothesis is false, and then we reject the null hypothesis. So that's a power. Okay, let me see this. Okay, let me say hypothesis first. So when you use a statistical test, you must know the hypothesis. You must, very important. Otherwise, you cannot interpret your results. So we have like two types of hypothesis: null hypothesis and alternative hypothesis. So the statistical tests are all about testing null hypothesis. All about that. All about this one. Not about alternative. All about the first one. So with the what is null hypothesis? So no intervention effect, no group difference, and nothing happened. So that the effect is equal to 0. The mean difference is equal to 0. No difference. That's null hypothesis. Very conservative. It's really like a new drug and old drug. The effect of them are same. No difference. My intervention has no effect on the primary outcomes. That's null hypothesis. Alternative hypothesis, absolutely against the null hypothesis, is my intervention, yes, had effect on the primary outcomes. Yes, there is a significant difference between two groups in primary outcomes. So alternative hypothesis is against null hypothesis. So the power is the probability of correctly rejecting the null hypothesis. So we reject the null hypothesis, absolutely we accept alternative hypothesis. So we state, hey, our intervention had effects on the primary outcomes. So power is really like when our intervention truly had effects on the primary outcomes, and then we get that kind of effect. It's, yes, it is. It is our intervention. Yes, had effects on the primary outcomes. So when null hypothesis is false, we reject the null hypothesis. See, that's the power. Alpha level actually in social science research, we always use 0.05. I think you have heard about that. Okay, alpha level is 0.05. What is alpha? Is the probability of making a type 1 error. Beta is a type 2 error. Alpha is type 1 error. So what's the meaning of type 1 error is when no hypothesis is true, means no effect, we reject the null hypothesis. That's the probability of rejecting true null hypothesis is type 1 error. So 5%, we use 0.05, like the probability is equal to 5%. 5% actually is a really small percentage. So we use it 5% as a cutoff. So for example, I get a p-value equal to 0.04. Is lower than the alpha level. So we reject the null hypothesis. We accept alternative hypothesis. Hey, my intervention had effects on the primary outcomes. So that's the way to interpret the results. So when you, drug companies, when they study new drugs, their alpha levels is lower. It's not equal to 0.05, 0.01. So you need to think about it, why they use 0.01. Why? Because type 1 error from 5% to 1%, you allow to have to make a type 1 error is 1%. Why? So it's really like they make rejecting a null hypothesis more difficult, right? Because think about that, my p-value equal to 0.04. If alpha level is equal to 0.01, I cannot reject the null hypothesis. I cannot. Yeah, I accept the null hypothesis. No effect, right? So when the bar is higher, the rejecting bar is higher, the alpha level actually is lower, then it's more difficult. It's more difficult to reject the null hypothesis. Why? Because when you study a new drug, the consequence, especially the drugs for human beings, the consequence is really severe. That's why we should be conservative. That's why the alpha level, the bar, the rejecting bar should be higher. That's why. Okay, but in social science, we use 0.05 is enough. Effect size is the magnitude of the effect or the difference. So it's we use different measures to measure effect size. So we can use Cohen's d, Hedges g, odds ratio. So Cohen's d, Hedges g, they are all about what? They are all about mean difference. So when you compare two groups in mean outcomes, mean difference, actually standardized mean difference. Standardized mean difference is effect size, the size of the effect. The size of effect. That's effect size. So when you estimate your sample size, unfortunately, you have to tell software, hey, my effect size is equal to what kind of value? This part is very challenging. It's really, hey, I don't know. I don't know the size of the effect. I have no idea. So you have to look at the literature or based on your own experience. You have to provide effect size. So I'll show you. So odds ratio is really like when your outcome is a binary variable, like a yes and no, then you can use odds ratio as effect size. Sometimes we use R square in linear regression. We use R square as effect size, or you use a correlation. Is the square root of R square is like correlation is your effect size. And then you need to tell the software what kind of test I'm going to use. So steps of conducting power analysis. Define research questions. Oh yeah, this is very important. Don't forget this. You should have your research questions first. And then plan the statistical test, make decision about what kind of test I'm going to use to answer my research questions. Choose effect size. Yeah, this part is very challenging. And then choose alpha level and the power. So commonly we use, I give you values, we use 0.05. Also we use 0.8 as power. Here, I just want to tell you, sometimes, when you estimate your effect size, You don't need to say, hey, my effect size, when you estimate your sample size, it's not say, hey, I need 200 people. Well, you can actually you can give people a range. It's really like based upon different effect sizes or maybe different powers. Hey, I can give you a range. So I need maybe between 200 and 300 people. See that? So I'm going to use R to show you how to do power analysis in R. You should have it. So right now I'm using RStudio. You can open RStudio, then you get something like this. In order to use RStudio, you must install R. So you must have R and RStudio installed in order to use RStudio. So I think you get the file here. You can watch. If you want to do it with me, that's fine. Because we don't need to read any data in. So that's really good. If you don't have this package, because in R we use packages. So I think maybe you don't have PWR package. You just run the line, highlight this one, and click run. You just install this package first. You need to do that first. And then activate this package. We use this function. So when you see something in blue, which means this is a function. Well, however, this is a function as well. I don't know, this one, not in blue. So anyway, let's activate PWR, this package. Oh, if you have any questions, use the chat. Okay, do you have any questions? Oh, okay, so. I only give you like 2 examples because I cannot show you all the tests, how to do power analysis. So I only give you independent sample t-test and the linear regression model. When you look at the published papers, the problem is people don't mention the test they use to estimate the sample size. They don't. You just look at public papers. I don't recall I see a paper. Hey, I'm going to use independent sample t-test, and then here is the power, the value of the power, and then they give you the value. No, I don't like it because really you hide something. Maybe they don't hide something. However, it's really you hide. You don't want us to know what kind of test you used. I don't like it. Okay. So independent sample t-test. What is independent sample t-test? Is compare 2 means. Only 2 means. When you compare more than 2 means, you have to use ANOVA, not independent samples t-test. You must compare means. Okay. So here D is coherence D. This is effect size. So I use coherence D. Coherence D suggests D value 0.2 is a small effect size, 0.5 is a medium, 0.8 is a large effect size. It's up to you which one you use. So if you are not sure, you can play with it. So I use 0.25, for example. And then my alpha level is SIG level is 0.05. You can play with this one as well. You can use 0.01. And the power is equal to 0.8. So this is the t-test, see t-test. And the type is 2 samples and 2-sided. So please don't use one side, just use 2-sided. I highlight the whole thing and then I click run. Because I created this new object, it's called PA1. So I just highlight PA1. Actually, it's like a print PA1 for me, like that way. So just run PA1. So I get this. This is the sample size. I need 252 people. Wow. And N is a number in each group. Wow. I need 500 something, right? 504. So let's play with it. How about the D is, let's change your effect size to 5, 0.5. Remember 0.5 is like a medium effect. Let's see what will happen. So I only need 63 or 64. Let's say 64 people each group. Is 128 people, 128 people in my total sample size. You see here, when the effect size is large, you don't need a lot of people. Absolutely, you can play with it. You even can change power. Absolutely, if the power higher, you need more people. So now, so you need this for each group. For each group. So, so this is an independent sample t-test. How about regression? Regression here. For linear regression, you need to tell R how many predictors in your model. So absolutely, I only have one key predictor. I have a group. However, because in medical research, we always control for demographics. So in my model, I have like a group. Group means intervention or not. That's a grouping variable. Also, I have like age, I have sex, I have the blood pressure, blah, blah, blah. I have so many things. Together, you need to count how many predictors. So I have like, for example, I have 3 predictors. Then U equal to 3. This is F square. However, yeah, because this is a coding, so we use F2, is F square actually is equal to 0.15. This part is not R square, is not. It's similar, but it's not. So for the F square, values of 0.02, 0.15, 0.35 represents small, medium, and large effect size. So for example, 0.03, that's a large or a medium or small effect size. 0.0, 0.0, well, it's between, okay, 25, for example, 0.025. I mean, it's between this one and this one is small effect size because it is not equal to this. Between this value and 0.35 is medium effect size, okay? So this F square equal to 0.515. Alpha level 0.05, and the power is this. So this is a F2 F square test. So it's a linear regression. It's a linear regression. You see here, different tests, absolutely, our programming is different. So you should tell people what kind of test you use to estimate your effect size. Let's see this. So we need, this is the V. Actually, V is what? Is degree of freedom. So degree of freedom is equal to total sample size minus the number of predictors minus 1. So if you want to get the total sample size, absolutely this one plus number of predictors and plus 1, then we get the total sample size. So let's do it. We get 76, actually 77 cases. So because in intervention research, dropout or attrition or mortality is very common. So especially, hey, my dropout rate is like 20%. So maybe your question is, why is 20%? Well, this number is commonly is 20%. However, maybe it depends on your own research. Maybe your dropout is lower, maybe higher. So when you estimate sample size, you have to take this one, I mean the dropout rate, into account. You have to think about this one. So I need 73 here, no, 77, I'm sorry, 77 cases. I need 77 cases. So my dropout rate is 20%. Then actually I need 97 cases instead of 77. I just collect data twice, two times. I don't need, so I don't have a post-test two. And then I need 97 cases. 97 cases. The dropout, you need to think about this. You need to think about this. So I know that is also depends on your data analysis. For example, if you use repeated measures, I know repeated measures. We have repeated measures. Why? At the baseline, you collect, for example, blood pressure. I collect blood pressure data at baseline, also at the post-test. So for each person in your data, that person has two columns, right? Column one is baseline blood pressure. Column two is post-test blood pressure. We call them repeated measures. I know that the data layout is in that way. That's fine. Actually, for longitudinal, we use different data layout, but today I'm not going to talk about that. But just picture it. So I have two columns. Column one is blood pressure at the baseline. Column two is blood pressure at post-test. So everybody has like two columns, and then we call them repeated measures. So you can, when you use repeated measures at ANOVA, and then people who didn't answer post-test won't be in the data analysis. I mean, common, won't be in the data analysis. No. So it's really like there is a dropout, then there is a missing, actually. There is missing, then this case, bye-bye. We want you in the data analysis. I mean, repeated measures, ANOVA, for example. Let's see this is power analysis. Now let's see the paper I sent to you. So this paper is about effectiveness of a mobile intervention to reduce young adults' alcohol consumption. Okay, so let's look at the methodology. Look at the power analysis. We just look at the power analysis. When you look at the power analysis, you see here an effect size of a G. I guess is a Hedges G. I just guess. So it's a Hedges G 0.25. So Hedges G equal to this, and alpha level 0.05, power 0.8. Then the sample size is this. So I guess is independent samples theta. That's my guess. So, however, no test mentioned here. No statistical test is mentioned here. No. You don't know. I just guess. It's independent sample t-test. It is very possible because Hedges G is about mean difference. Mean difference. Okay, so our analysis. Randomization. We randomly assign people to either group, and this is a key of RCT. So sometimes when you know your confounders, and then the randomization is called stratified randomization. Is like this. I have two confounders, sex and age. So each variable has two categories, like this. And then you can combine this is two category here. When you combine two variables, then you should get the new variable has four categories, 2 times 2. So you see here, we got four categories here, 1, 2, 3, 4. So we have two groups here. So you need to randomly assign participants to each group. See that? So you see here, male younger than 18 years old, 10 cases. In intervention group, in placebo group, also 10 cases. Absolutely, you can use Excel to do that because we can use random numbers to do it. You can use Excel. However, I prefer R because we will use block randomization. Please use block randomization. So block randomization, what is a block randomization? So it's a technique used in experimental design RCT to ensure that treatment and the control group are balanced at regular intervals. So I have two blocks. So each block, group, intervention group and the control group, has equal sample size. So let's see how to do it. So this is the R code for the block randomization. So we use this package, it's called the block rand. Yeah, you need to install this package. Just highlight this, click run. I already have it. If you look at the packages here, see I have it, block run, I have it. So let's activate this one. So how to use this package? So first you need to know something. So for example, I know my sample size based upon power analysis. I need 20 people. Okay, this is a fake number. So I need 20 people, and I should have two groups, intervention group and a control group. So the total sample size is 20. So each group should have like 10 cases. So the ratio of a group size, two group sizes is 1 versus 1. So 1 to 1, and then 10 in each group. But sometimes we use 1 to 2, it's up to you. So the block size is 4. What's the meaning of that? So each block has 4 participants. So just within this block, we need to randomly assign 4 people to either group. See that? So that's the idea. So the block size is 4. Well, maybe you say, hey, can I use something else? Yes, you can. Yes, you can. So now my example is block size is 4. Okay, because this is really tricky here, I hate that, but however, be careful here. So for example, we tell the block size here, we use C function here is, hey, my block size is not 2 or 3. I should have 2 types of block sizes, either 2 or 3. See that? Actually, in reality, is not 2 or 3. In reality, should time to 2. Should be times the number of levels here. Number of levels means the number of groups. So your time number of groups, so we should have the block size is 4 and 6. So if you don't tell R, I'm not going to tell R my block sizes. By default is 2, 4, 6, 8. By default, you can give a try. It's really like just delete the line of code here, and you can see what will happen. So the block size should be 2, 4, 6, 8, because by default block size is 1, 2, 4, and then times 2 because we have 2 levels, and then 2, 4, 6, 8. So levels here we tell R. I have intervention group, and also I have a control group, 2 groups. And the block size is 4 and 6, so we use this 2 and 3. ID, so here we just give us, because we will get columns, we just tell R the column name. So let's see. So we cite seed 1, 2, 3, because this is random. Remember? Random. So each time you run this, you get different results. Yes. So we use set seed. This seed number is 1, 2, 3. You can use any integers. So here we just want to make sure every time when I run this, I should get the same result. So that's why we run this line of code, and then we run this. And just print BR. So we get that. So we have 20 people. So that's a sample size here, 2 groups. And we have, you see the size is 4 and 6. Yeah. So in some blocks, we have like 4 participants. In some blocks, we have 6 participants. So in this block, we have intervention control. So this is block 1, is the first block. The block name is 1, block 1. So the participant 1, 2, 3, and then your is like the intervention control intervention. 4 participants randomly to assign to either group, and the ratio is 1 to 1. So for the block 2, we have 6 participants. So here, from here to here. So you see, control intervention, control intervention is very random. It's random and random. It's random. So we have a third block. We also have 6 participants. And then we have last block. This block, we have 4 participants. So yeah, you can use this user result to assign your participants. So here, when I see this, instantly I know, okay, this is like a data. It is like a data. So I ask R if this BR is a data frame, because in R, we call data set is data frame. So let's see. So true means yes, it's a data frame. When we get a data frame, absolutely we can export this one to what? To my computer, my local computer. We can create an Excel file. So this is the package we should use to convert this one, the R data from R, the data from R to Excel, and also save this file to this location, this C drive, blah, blah, blah. This is about location of the file. So this is the file name, my data. This is Excel file. So let's do it. And then I do this. But let's see that data file. This is my data. Yeah, this one. Let's see. Oh, it's so slow. This is Excel file, it's nothing else. Uh-oh. Yeah, here we go. So you get this Excel file, this is the ID, your participant's ID, and then block, in which block. Actually, the most important thing is this. So the first participant should be in intervention group, control group, intervention group. So you can use this file to do the randomization, not do the randomization, to assign your participants to either intervention or control group. Okay. So now if a sample size is not even, because 20 is an even sample size, so I have 23 cases, and then we do the same thing. So here I didn't tell R what kind of block size I need. I didn't tell. Let's see. Then I get this. I remember that by default, the block size is 1, 2, 4. So we have 2 groups, so it should be 2, 4, 6, 8. So let's see 6, 2, 4, 2, 8. Really good. So we get the very similar results. So maybe you say, hey, I only need 23. Oh yeah, that's fine. Just stop here. You only just stop here. You can forget about 24, 25, 26. You only need 23 cases. Then you just stop there. Okay. So if the ratio between two groups, intervention and the control group, it's not like 1 to 1, it's 1 to 2. I have like double the cases or more cases in control group. Actually, you do is you treat your number of level as 3. So intervention, control. You see that? So here you see intervention, control, like 3 levels. So if you need more cases in intervention, then you change control to intervention. And then the block size, I say, hey, give me 2. Actually, you can change block sizes. Yeah, you can do that because I use different sizes. So you get this one. So because the size, only one size, so only equal to 6. So 2 times 3, number of levels. So the block size is 6. So we have them. You see here, intervention, control within this block of 1. So within this block of 1, we have 2 intervention and 4 control. 1, 2, 2. See the ratio here? So if you are not sure, I'm going to use this table function to look at distribution of this treatment variable. This is a variable. Let's see. Okay, so 30 cases, so 20 in control and 10 intervention. Yeah, that's good. The ratio is 1 to 2. This is good. So here, when we have confounding factors, I have like sex and age. So this is more like a block randomization with stratas, with is like a stratified randomization. We also have block. So here I have like 2 confounders, sex and age. So sex has 2 categories and age has 2 categories. So I combine them and I get 4 categories. It's like a male younger, male older, female younger, female older. Absolutely, you have a cutoff. For example, I'll use 18 years old as a cutoff. Younger than 18 years old is younger, and equal to 18 years old or older than 18 years old is like older. So each category has 20 cases, so the total sample size is 80. So when you have confounders, you have to do this. You have to do block randomization by each category. So I give you example is, for example, this is a female younger. I just focus on this category, female younger. So I have 20 cases. Also, I have 2 levels, intervention and control, right? Yeah, just female younger and assign people in this category to either intervention or control group. And then I do the same thing for male younger, and then you do female older and male older. So you should do 4 times. So I only show you I'll say that. I'd only do 2 times. Why? Because 4 times too much. So you can play with it, you do 4 times. I only do 2 times. I just do the block randomization for female younger and for male younger. Actually, the code is very similar. The sample size 20 for each category is 20. The number of levels, 2 levels. Intervention control ratio is 1 to 1. And then block size is 2. So let's do it. And then we get this, let's see this, the results. So this is just, you see, male. Oh, this is male younger, I'm sorry. Yeah, we should have female younger, that's fine. So you have male younger, that's for male younger. So 20 cases. We do the same thing for female younger. So we get this. So you should keep doing for male odor and for female odor, do the same thing. And then after you finish everything, combine your data files. Yeah, you need to, because I only want one data file. So how to combine them? So we use this one, we combine two randomization results. So we use a tidyverse package. And I create a new project is just combine the rows, because yeah, you should combine rows, not columns. We column same. The column, the variable name here, they are same. So we just combine rows. So that's why it's bind rows. So now we need to do is export them to create an Excel file. So I run that. So let's see the data. My data one is here. So this is my data one. You see here that's female, younger, male, younger. And we should do like 4 times. So we should have male, older, female, older. You all combine them, then you get the treatment. I mean the group membership. Is it intervention group or control group? So that's a block randomization. R is very convenient. Close it. Okay. This is so my recommendation is please use block randomization, and when you have confounding factors, you put the confounders in. So for example, hey, I have a lot of confounders, so don't do a lot. Actually, 2 or 3 should be enough. When you have really a lot, then it's difficult, it's challenging. Think about that. I have like 3 variables. They are all confounders. Each variable has like 2 categories, and then the new variable should combine them. 2 times 2 times 2, 8 categories. So I have 4th variable then. So too much. You just pick the most important confounders. So cluster randomization is really, I have clusters. I can randomize my cluster. Not very good. I said, for example, a classroom. So I'm not going to randomize my students in each classroom. So I just randomize classrooms. So classroom A, classroom B together, and then randomize them. That's not very good. However, sometimes we have to compromise. Blending here, blending is, so everything we do, randomization, control group, we try to enhance internal validity. Blending is the same purpose, same purpose. We just try to avoid what the bias. It's really like other factors explain the results and not my intervention. So blending is we have like a double blind. Both the participants and the researchers don't know the group memberships. So we don't know this group of people, oh, you are in control group, oh, you are in intervention group. So we don't know. Participants don't know, researchers don't know. So I think that the people who do the data collections, they don't know who, and also the people who conduct the intervention, they don't know. Well, maybe they know. So because the interventions are different, but they know. If only one party or either participant or research is blinded to the treatment, the study is called single blind, double blind, single blind. Well, study is like a no blending, we call that open, no blending. So let's look at the paper here. So in this research, you see the randomization here. So let's look at randomization first. So in this research, there are two groups. So you see participants were randomly to receive either the intervention condition or the minimum active control condition. So in this paper, the control is a website. You go to the website, take a look. That's a website. And intervention is a mobile or something. So you see here the ratio between two groups is 1 to 1, and the block size is 4 and 6. That's really good. You have like a, because the sizes are different, is much better. Absolutely, much better. And stratification was based on sex and adherence to the drinking guideline. So they have like confounding factors. So that's a randomization. That's good. I love this. Very clear. On the blending here, they say, okay, let's see the blending. Where is? I think there is something, is no blending, no blending. Here we go. Due to the nature of the study design, blending of a group allocation was not possible. So no blending here. No blending here. So who should be blended? Participants, researchers. Well, sometimes data analysts, when they do data analysis, they do know. Well, it's it's a, I don't know how to blend the data analysis, because you give me data, you tell me the coding, so I know the coding. So this is group 1, group 2. So group 1 is the intervention group, and the group 2 is group control group. Well, you don't tell me the coding, I just run data analysis. You don't need to know the label for the coding. Well, that's fine. The purpose of blending, I said that, is all about internal validity, all about that. Don't create a biases. No. So because when researcher know, hey, you are in intervention group or you are in control group, maybe subconsciously treat you differently. When participants know, hey, I'm in intervention group, in control group, they perform maybe differently. So that's why we try to avoid that kind of bias. When you know the group membership, when you look at the results, or maybe not the results, results. Maybe you look at the result, maybe you interpret the results differently. So that's why we need blending. Attrition here. So the high dropout rate is greater than 20%. So we need to study, in data analysis, we call them missing, because you don't have this case drop out at the post-test, or missing in the data. In the data, we see missing. So the strategy is to reduce attrition, not just the one I mentioned here. Maybe you have your different strategies. I just give you some examples. So you track participants list, their name, their age, phone number, email address, blah, blah, blah. Even their home address. You just try to locate them, try to get them. And also you reduce participants' burdens. Usually like, you provide transportation. For example, I do intervention at the hospital, hey, you provide transportation, the schedule is more flexible, something like that. Or even you give money, we call that is like incentive in research. You give it like just give money, cash, something like that. Or more communication, you call them, you want to know why they didn't come to the post-test, something like that. You do follow-ups. A lot of strategies, but it is not easy. Trust me, it is not easy. Hey, people, you collect data here, but people move to another state. But the good thing is right now we can do something online. However, when you do intervention, sometimes you cannot do it online. No. So we need to assess the patterns of missing, because when missing, we can assess the pattern of missing. So we have like this MCAR is missing completely at random. It's really like the dropout is unrelated to any observed or unobserved variables. It's very random. The dropout is very random. No reason. No reason. I mean, no systematic reason. No, just very random. So that's MCAR. Actually, is really good. This is good because we have strategies to deal with the MCAR. Missing at random, dropout is related to observed variables, but not missing data itself. So what's the meaning of that? We have missing in income. So missing is income. So the missing is related to age, not income. Okay? So older people are less likely to report their income. So this missing related to an observed variable, age, not income per se. Okay, not income. So that's MAR, missing at random. We also have missing not at random. This is a nightmare. Absolutely. I'm NAR. So dropout is related to the missing data itself. We study income is related to income. So people with higher income are less likely to report their income. That's MNAR. We deal with the different types of missing, absolutely different. So we can how to handle missing data. We can remove missing data. Just remove you. Bye-bye. You are not in data analysis. We have a list-wise deletion. List-wise deletion is only complete cases are in the data analysis. So I have like several variables, and then you have you're missing in one variable, you are removed. You are removed. Not good. Don't do that way. Don't do that way. No. And this is called list-wise deletion. Pairwise deletion is, hey, for example, I want to study the relationship between A and B. A and B. So when there is missing, yeah, somebody is waiting at lobby. Please let that person in. So pairwise deletion is we study relationship between A and B, so that when missing in A or in B or in both, and then that case won't be in the data analysis. So then pairwise deletion is not like, hey, you have missing one variable, I delete you from the data analysis. It doesn't matter, are you that variable or not? This is very common in data analysis. Pairwise deletion is very common. So when you have a data with missing, don't delete missing. Do not delete cases with the missing. Don't do it. Unless it's really like a whole row is missing. It's totally missing, like no answer. Whole row is missing. And like no valuable information. So also we can impute missing data. So commonly we use this impute missing data in data analysis. So we can replace the missing with imputed values. So we can replace missing data with a mean and a median. Also can do regression imputation. So we can predict that missing data based on other predictors. Or we can do multiple imputation. Actually, the last one is the one we use. Is multiple imputation. It's really like we ask a software. Software can do it. We ask a software to do it, to impute 20 data sets for me. 20. Even you can ask 100. Create 100 imputed data for me. And then your data analysis based on all of them. Based on all of them. Because the software can pull the results for you. So that's a multiple imputation. You see here, median mean is you have like MC is completely random. Absolutely mean and median should be okay. Or MAR, just add random. But for NAR, please use multiple imputation. Multiple imputation. Treatment and intervention here. When you develop your intervention here, you very possible you use we call that mixed research design. So you use a qualitative research design to collect information, right? For example, you want to know people's, we do focus groups or individual interviews, their opinions about your intervention, or you want to create your intervention materials, you interview them, you do group interview like a focus group, or you do individual interview. You try to come up with your intervention materials. Absolutely, you need to use your targeted participants. Hey, I want to study undergraduate students at ECU. My intervention for them. So when you try to do focus group or individual interviews, you collect data from them, from ECU undergraduate students. You see that? So if somebody in your focus group or individual interviews in the future, they won't be in your intervention research. They won't be because they're already exposed to the intervention. Also, we can pilot testing intervention materials. We can use a focus group, or maybe use quantitative research because we collect data from small groups, very small group of people. You need to develop a protocol. So the protocol is really all about how to implement your research. This is so important, so important. And your interventionist must follow the protocol. They can. So I remember one person told me, "Hey, my intervention is not good. Went wrong. What's going on?" Because one interventionist added her own stuff to the intervention. You see that? That's not good. So everything here is about internal validity. And at the end of the day, we just want to know whether or not my intervention truly had effects on the outcome. That's why. So outcome measures. So here I give you 3 types. So you want to do is, for example, equivalence is really like, I just want to compare 2 groups. I want to point out the direction is one group is better. My new drug is better than old drug. My new treatment is better than the old treatment. So you see here the superiority. This one is really like, hey, my new treatment is better than old treatment. So this one is my new treatment is not worse than the old treatment. You see that? So what can actually I prefer equivalence to give you at least you are very sure. You are very sure the direction. So primary outcomes and secondary outcomes is really like this is the primary outcomes, absolutely main outcomes. Main outcomes. Yeah, I give you examples of primary, secondary outcomes. Data analysis, data layout. Here, I would say multivariate data layout, univariate data layout. When you have more than 2 times, you collect data more than 2 times, please use univariate data layout. What's the meaning of that? Each person has more than 1 row. Multivariate data layout, each person has only 1 row. Only 1 row. They're different. So data layout for longitudinal study, univariate data layout just for, so for example, I collect data twice. Multivariate data layout. So for example, I collect the blood pressure. So baseline blood pressure, 1 column. Post-test blood pressure is another column. In univariate data layout, is like you only have 1 column called blood pressure. And then you have another column is called time. So time 1, time 2. See that? You can picture it. Because this part is so important. That's why I moved maybe a little fast. Yeah, this part is very important. So this is called intention to treat, ITT. In medical field, when you look at the published papers, you see this term. So what's the meaning of that? In ITT is really like in the data analysis, everybody is in the data analysis. I don't care you didn't complete our post-test. I don't care, but you are in the data analysis. You are. So absolutely, how do this? Absolutely, we can impute data. Then everybody will be in the data analysis. So ITT is preferred data analysis. It's preferred. It's not like, okay, you didn't come to the post-test, bye-bye, I won't use you. That's not recommended. So you see here, ITT, all randomized participants are in the data analysis, reduce bias, absolutely. It avoids overestimating the effectiveness of an intervention. So ITT is preferred and also provides strong evidence for the intervention's effectiveness. So use ITT. Everybody should be in the data analysis. So it's a challenging. Why? Because you have to deal with the missing. You have to. How to deal with missing data? Multiple imputation. I said that. Another one is you use multi-level modeling. When you use multi-level modeling, the beauty of a multi-level modeling is you don't need to worry about missing. Hey, I collect data. So multi-level modeling is really like you don't have a single level model. For example, linear regression is like a single level model. Multi-level model, you have a level 1 model, also you have a level 2 model. So you model the random effect. So today is not about this, but just give you some ideas. So in longitudinal data, we use a multi-level model. Actually, everybody will be automatically in the data analysis, even though we have missing at time 1, at time 2, time 3, time 4. It doesn't matter. I collect data 8 times, so one person only give me 1 time data point. That's fine. That person is still in the data analysis. We use multi-level modeling. So that's ITT. Keep this in mind. This is the preferred data analysis. So how about PP is per protocol? So in PP is really like you drop out, bye-bye. You are not in data analysis. Only the people who finish everything in my data analysis. So you see here, excluding participants breaks the randomization balance, absolutely. Especially the dropout between 2 groups is not balanced. Hey, more dropout maybe in intervention group or maybe in control group, and maybe more older people drop out, then you're missing is not completely at random. So if you use PP and then the result are not reliable. Here is the table about comparison between ITT and the PP. You see here, all randomized participants in ITT, only adherent participants. Yeah, that's right. No dropout people in the data analysis. So we all estimate effectiveness. This is real world, and this is ideal conditions. I don't know why it's called ideal conditions. So, and the bias, we minimize bias by preserving a randomization and the risk of selection bias. And general ability is very high, and this is low. We cannot generalize. Why? Because the missing is different. Every time missing is different. The reasons behind the missing is also different. Are different. So we cannot generalize the results to other populations. I mean, the same population maybe. So often required for primary analysis. So in primary analysis, we use ITT. So here, use as supplementary analysis. I see that people used PP for sensitivity analysis. I'll talk about sensitivity analysis. There is assay. So in sensitivity analysis, we can use, some people use PP. So what's the sensitivity analysis? It's really like conduct sensitivity analysis to assess the robustness of the study results. So basically, I can use subgroups. I study subgroups. So I gather results from my whole sample. Hey, I just want to focus on female. What happened? Whether or not my intervention still had effects on primary outcomes. So that's a sensitivity analysis. Or maybe you use different cutoffs. So I have something here. Yeah. So types of assay. Compare ITT results from ITT with the results from PP. If they are consistent, which means the intervention, yes, had effects on the, well, if your conclusion is my intervention had effects on primary outcomes, and then that's true, because you get the same results. The definitions of outcomes, you can perform data analysis on outcomes with the different definitions or cutoffs. I think cutoffs is very common. You can do is for outliers. Without outliers or with outliers, what happened? So outliers is not like they are, sometimes people deal with outliers really like, okay, they are outliers, they are not true responses. Well, sometimes I keep outliers. Why? Because they are very possible they are true responses. They are true responses, even though they are outliers. Also can do subgroup analysis, test if results are consistent across different subgroups. So they are all sensitivity analysis. In medical field, when you look at the published papers, they reported IDD results, report sensitivity analysis. Some people reported PP results. There we go. So for the data analysis, I give you a list of data analysis here. So you can do repeat measures, ANOVA, MANOVA, linear regression, structural equation modeling, and multi-level modeling. Well, the first one and the second one, when you collect data only twice, baseline, post-test. You can use repeat measures, ANOVA, or linear regression. I collect data more than 3 times. Then you should use a multi-level modeling. Usually at least 3 times you can use a multi-level model. Equation, structural equation modeling actually is okay too. For you collect data twice or more than twice, you can use SEM. So today is not about data analysis, but just let you know, you have several choices. However, very complicated. Why? Because you have to deal with the missing. You have to deal with the missing. That's very challenging. It's challenging. So if you say, I don't want to deal with missing, go ahead, use multi-level modeling. In multi-level modeling, especially because you have repeated measures. When you have repeated measures in multi-level modeling, time is a predictor because you want to see the change over time. So time is a predictor. So issues for the RCT treatment fidelity. So treatment fidelity refers to the methodological strategies used to monitor and enhance the reliability of behavioral interventions. So it's really like treatment fidelity is about whether or not the treatment or interventions are delivered as expected. So it's really like whether or not interventionists or people who do interventions follow the protocol. This part, so that's why you have to monitor an intervention. So we call that like a process evaluation. You evaluate interventionist's performance. You have to. Otherwise, if they use their own language, they don't use, you have protocol, it's really like you have like a transcript. You need to read that transcript. So it's don't use your own language. You have to train them. You have to train them before data collection. I mean, not data, before the intervention. You have to train your interventionists, make sure they follow the protocol, and also tell them the importance of following the protocol. This is so important. It's all about internal validity. Randomization is not random, so you use software should be fine. And if you use Excel, I use Excel, I created random numbers, okay too. It's okay too. Underpowered study, you don't have enough samples. This absolutely, I think this is also a big issue in quantitative research. You won't get enough people. Even though, hey, I need 500, impossible to get 500. So try your best. Try your best. And a high attrition rate. This is also a common issue in RCT. Well, you need strategies before you do any data collection. You need strategies to avoid high attrition. You totally avoid attrition, maybe impossible. However, try to avoid a high attrition rate. So just lower your attrition rate, dropout rate. Okay. So let's look at our example here. The paper, you have this paper. So this paper I said is about, is like RCT design. Let's see the design. So I'm not going to read the introduction or abstract. Let's look at the methodology. That's my focus. So we conduct, so in this study, we conduct two arm. Two arm means two groups, parallel group. So two parallel group means it's really you collect data at the same time. Randomized control trial, RCT design. So comparing a 6-week self-guided mobile application. So this is called the Booze Buster. So this is the intervention's name. And compare it with an educational website condition. So website condition is a control condition. So they gave control people something, a website, educational website. You go ahead, read something there, over there. So I decided due to the nature of the study design, blending of the group. So no blending. So randomization, where do you know? And sample size, where you know. So the same problem here. I have problem with the published papers. So that's my personal problem. It's really, they don't mention, they don't mention what kind of test you use. I have no idea. Even people, so if people are not familiar with the hydrous G, I don't know G. What's the meaning of G? So they don't mention that. Not good. So let's look at the intervention here. Okay, hold on, let's see. Okay, let's look at the intervention here. The developmental process includes several steps involving the potential and the users. You must use your targeted population, a target sample. which include interviews, brainstorm sessions, and the focus group. Yeah. So qualitative research absolutely is here. So intervention research, sometimes we call that mixed research design. Why? Because we have before data collection, during data collection, after data collection, I have a qualitative research component. So it's called mixed research design. It's not just RCT. So in RCT, you have a qualitative component. So you know that they use interview, brainstorm, focus individual interview, and focus group with the group interview, and also brainstorm sessions to develop their intervention. Okay, so assessment here. So now I want to know the timeline here. What kind of timeline? So participants of both groups were invited to fill out questionnaires at the baseline. They call T0, it's time 0. 6-week post-intervention, that's time 1. And 3 months follow-up, that's time 2. So collect data 3 times. See that? So keep this in mind. Time variable is important. Time variable is very important in this kind of research, in intervention research, especially you collect data more than 2 times. So the primary outcomes is at intervention, so the frequency and the quantity of alcohol consumption. Secondary outcomes, binge drinking frequency. So you can take a look at the table here. This is really good. So at the baseline, they collect data for every single measure. Social demographics, that's demographics. Alcohol consumption frequency, that's primary outcome. And the binge drinking, that's a secondary outcome. I think this is also secondary outcome. And then after 6 weeks, they collect data again. So all of them except demographics. And after 3 months, then collect data again. Only alcohol consumption, binge drinking, and alcohol-related problem drinking. So only 3 measures, others, no. So it's not like every measure has 3 time data points. No. So the moderator in this research data, there are moderators. So the moderator, what is a moderator? Moderator, for example, sex is a moderator, which means relationship between, let's use an example here, which means the relationship between grouping variable. The grouping variable is what? Is like intervention control. That's we call that grouping variable. Between grouping variable and alcohol consumption is moderated by including sex. You see the sex by sex. So it's really, in other words, the relationship between, or you say intervention effect on frequency of drinking and quantity of drinking is different. It's different across different levels of sex, or among females and among males, they are different. The relationship is different, or the effect of intervention is different. So that's a moderation effect. So the moderator here, including sex, the motivation to change alcohol use behavior, and the engagement with the intervention and the treatment adherence. So for the control, something like this. So that they are moderators. So the sentence here, see that several potential moderators were assessed that could affect the effect size, the use effect size. Well, it's okay, absolutely it's fine. However, I think for people, if you don't know much about effect size, this really is mind-boggling. Actually, effect size, think about effect size, mean difference effect size. So it is about, actually in this study, in this paper, the focus on is mean difference. We want to know the mean difference between 2 groups. That's the main focus. That's why it's called the effect size regarding the primary outcomes. Actually, I prefer it's just intervention effect, intervention effect. And people instantly understand regarding the primary outcomes. Okay. So there are moderators in the data analysis, and so now it's a statistical analysis. So data analysis is performed using SPSS, and then for the demographics, they compare. See this? This is about demographics. So baseline characteristics of participants. Yeah. So they compare demographics by two groups. So they have like a t-test or chi-square. This is really good. So when the outcome measure is a continuous variable and then is a t-test, I think for the what is that? For the let's see, alcohol use. So alcohol use, I guess, is a continuous variable. So they give you mean and standard deviation. I think, yeah, it's standard deviation. So for the categorical variable, so this education is a categorical variable. For a categorical variable, because you look at the association between one categorical variable, this grouping variable, and this education, this another categorical variable, then you use chi-square test. That's why you look at the education, even look at the sex, you get the chi-square value, and then you get a chi-square value, get a p-value here. So this is really good. You compare two groups. You want to know whether or not they are different in demographics. So because this is, you use randomization, this should be fine, right? This should be fine. Then to analyze the effects of, the effects of intervention on the primary secondary outcome. So by group, okay, linear mixed model. Linear mixed model also is also called multi-level modeling. Same thing, but it's linear. So linear mixed model analysis was conducted. So they have a random intercept and a random slope. And the data were analyzed using intention to trade ITT. And PP using sensitivity analysis. Yeah, so in sensitivity analysis, they use PP. Okay, so let's, and also they have like sex motivation, and they have moderators. Put the moderators also in the model, in the linear mixed model. So let's look at the linear mixed model results. Okay, before I look at that one, you see they have like a subgroup analysis. This is also like a sensitivity analysis. That's really good. They look at the problem drinkers and the binge drinkers. Yeah. Okay. So this table you see here, effect of the intervention on primary and secondary outcome measures. So I have problem with this. Because it's a linear mixed model, it's a linear model, you should give us regression coefficients. I don't see regression coefficients. They are not regression. I don't think so. They are means. I think is a means. So that this is the shortcoming of this paper. It's really like you mentioned you use a linear mixed model. However, I don't see any linear mixed model results. Nope, nothing. Even this one, this is subgroup analysis. We don't see that. No idea. They give you time 0, time 1 by each group. So what? I have no idea. You give me mean here. Well, I don't want to see mean. I want to see coefficient, because a coefficient can tell me the relationship between group and outcome. So here I don't get any linear regression results. I have no idea. This F value, and we get the D. I think that's the effect size, and yeah, D here, that's effects. So just effect size. They just give us effect size. Well, no, don't like it. You said a linear mixed model. Give me a linear mixed model results. We don't get linear mixed model results. No, nothing. So that's the problem. It's not just this paper. based on my experience, a lot of papers said, hey, we use a linear mixed model. You don't see the results of a linear mixed model. It's they even don't tell you we have it's a multi-level modeling. So you should tell us you have how many levels, 2 levels, 3 levels, because we can have 3 levels model. And they even don't tell us level 1 predictors, level 2 predictors. No, they don't tell us. They even don't provide, you see here, they mentioned we have random slope, random intercept. They don't tell us the value of random intercept, the random slope. No idea. So in the outcome here, they say, hey, regarding alcohol consumption, both groups show decrease around 17 units per month at time 1. That slightly increased over time 2. They give you just mean, they talk about the change over time by means, not by the regression coefficients. Don't like it. No. So I quickly show you the result. Then I'm going to stop here. This is the example of a linear mixed model results. So we can get estimates is time. So this is effective another variable. So time effect, effective effect, SES effect, and also get time by SES interaction. So also you get a residual. This is a random. This is a random intercept. We get a random slope. We get them. They are what? They are random, for example, random slope. Random slope is the variability. So for example, this random slope is for time. So this is the variability of this fixed time effect. How this time effect varied, this is the variance. So we don't get that. I know. That's why I don't like, but other stuff is really good. They're very perfect. They report everything related to RCT. So I'm going to stop here. So do you have any questions? Okay. Okay, no problem. Yeah. So later on, if you have any questions, you can email me. So I think that's it.
Thank you so much. That was
No
great.
problem.
And appreciate it.
People all left because too long. Okay. So thank you so much. Bye-bye.
Great. Thank you again. Have a good afternoon.